Hi guys, this is the second time I'm doing this because the first time it messed up. So if I sound a little bit mad, that's why. um, I want to explain a little bit about the modified Atwood's machine. So I'm just going to give you a little background on it. First of all, this is what a modified Atwood's machine looks like. You have some sort of cart or block that's on a table. We're going to be talking about a frictionless version, so there's no friction in this case. Then you have a pulley and a string, and then a hanging mass. We can call this big mass M, and this little mass or the hanging mass little m. In your lab, your goal is you're making this hanging mass bigger and bigger and bigger, and you're seeing how that affects the acceleration of the whole system. Um, you might predict that the more mass you put on the hanging end, the more it's going to accelerate. But we want to be able to quantify it, like how much can we calculate it? And so I want to show you how we do that. So the first step is that you're getting position and time data, and we've done this in class, so we're not going to talk about this too much. But once you get your position and time data, you graph it in a position versus time graph, and you see that you get some sort of curve. This is not very helpful to us. The only thing that's helpful about it is that the curve tells us that we definitely are accelerating. So we want to be able to capture that acceleration. And the way that we do that is by plotting the same thing, but we need to linearize it. The way that we linearize a square graph is by squaring the x-axis, in this case time. So if we actually add a third column here and do time squared, what we can do is we can square each of those values and then replot the graph as x versus t squared. You should get a line afterwards, and that is helpful because then we can find the slope of that line. The slope of that line ends up being 1/2 times the acceleration. The way that I know that is if I use the second kinematic equation, and if we're starting from rest, that's 0, and if we're starting at 0, that's 0. So then I have x is equal to 1/2 at squared, where x is my y. This is the equation of a line, right? And then this is my slope, and then this is my x, and then there's no y-intercept because it's 0 there. So that's how I know that the slope is 1/2 times the acceleration. And what you end up getting is a bunch of accelerations when you have different amounts of hanging mass. So what you're going to get at the end of your lab there is you're going to have hanging masses, and I think it goes like 0, 20, 40, 60, 80, 100, something like that, and that's in grams, right? And then you have accelerations, which you'll have some numbers for. Once you get 5 data points, then you'll be able to plot it. So you're going to see some value here. We have acceleration on the y and mass on the x, and you're going to get something that looks like this. Now this is the hanging mass that we're talking about, and the point is, so what does this mean? Well, let's look at some basic things. First of all, when you see a straight line, or especially a straight line going through the 0, 0, that means that these things are proportional to one another. Oops, proportional. When two things are proportional, that means whatever you do to one, you do to the other. So if I double the hanging mass, that's going to double the acceleration. If I half the hanging mass, that's going to half the acceleration, and so on and so forth. That's useful information for us because that helps us understand how this hanging mass is related to acceleration. Perfect. But of course, it's not that easy, and we need to figure out what is the value of this slope and what does it mean significantly or physically. Is it significant, and what does it mean physically? So what does the slope mean? And we mean physically. Like, what does it mean physically? So the way that we can figure this out is by first starting with the equation of this line. Remember, y is equal to mx plus b. That's the equation of a line. And because we're going through 0, 0, it's just no b, no y-intercept. And the equation of this line is a, because that's on the y-axis, is equal to the slope, which we'll call k, times the x variable, which is mass, the hanging mass. So here's the equation on my line. Now I'm going to draw this down here again, rewrite it for you. A is equal to k, which is the slope, times mass. We want to relate this because the thing that we're talking about here is Newton's second law. Newton's second law is A is equal to the net force over the mass. Now here's the thing. This m is the total mass. This m is the hanging mass. These are not the same m's, so I just want to clarify that to start with. So the question is, what does this k represent? Well, let's take a break here and take a look at some force diagrams on the modified Atwood's machine. So if I do a force diagram for each of these individually, you get gravity and normal, and these cancel, and you get some sort of tension, right? Assuming there's no friction going to the right. And then for the hanging mass, we have gravity going down, and then we have tension going up. These tensions are the same because they go along the same string, and they're actually action-reaction pairs. They're the same force, so they have the same magnitude. This Fg is the hanging mass, and then this Fg is the big mass, right? So this doesn't help us too much because we actually don't know what this tension is. So instead, what we're going to do is we're going to redraw the force diagram, but this time we're going to do it for the entire system. Remember I told you guys that we can define a system however we want to, and if I actually define the system as just these two masses, then we can draw a force diagram that looks like this. Gravity's going down, this is of the big mass, and I have normal going up, and that's just on this big mass. Any forces that are in the strings, these are called internal forces, and they don't get put on the force diagram because they're internal to the system. So only external forces do. So that's why gravity and normal, because the table is not in the system and the earth isn't in the system either. It's outside the system. So then the other thing we have here is gravity on that. Now we can't put this force over here because we have to draw all of our forces coming from this dot. So here's the question. Do we put it here like this, or do we put it here like this? Well, it's up to you. I personally like putting it to the left because it makes sense to me that this pulley is redirecting that force, so it's really just coming like that. And we could just call this Fg little m, and we can understand that it's really going to be pulling it left and down like that. If that is too much for you, you can just ignore that one and you can just put it on the bottom here like that. But either way, one thing is true. This gravity is going to be the net force acting on this entire system, right? If I said what's the net force of the system, it would just be Fg on the little hanging mass. And going backwards a little bit, we have this equation, this older equation. Let me write it in black. Fg is equal to mg, right? This is the weight equation. And so the equation for Fgm would just be mg. So this would just be equal to mg. And this is the little hanging mass. So the net force on this entire system is going to be the hanging mass times g. So let's revisit these equations up here. Let me get rid of this real quick. So the net force is equal to mg. So if k is equal to, let me actually write it over here. If k is equal to g over the total mass, and I plug that in here, g over m total, times mass, hanging mass. This right here is the net force, and then this is m total, and what you're left with is this, which is this. So what we're looking at here is Newton's second law as well, where k is g, which is 9.8, divided by the total system mass. So that's cool. That's what the slope means. It means that it's g over m total. So just as an example, let's say that your slope was I'm just going to make something up, 200. I don't even know if that makes sense. Then that would mean that 200 is equal to 9.8 over the total mass. And so that means we'd be able to calculate what the total mass is just by using the slope. So that's really useful to us. All right. I'm going to stop my thing here, but basically the equation of acceleration of a modified Atwood's machine is just the net force over the mass. It's Newton's second law, but specifically this is the total mass, so it's the net force over the big M plus the little m, because that's the total mass going on, right? And then this net force, if there's no friction, then the net force is just, and this is for the total system, right? Um, then the net force would just equal the Fg of the hanging mass, which would be the mass of the hanging mass times g. So we could replace that and say the acceleration of the total system is equal to the little m, the hanging mass, times g, divided by the big M plus the little m. And that, again, is just a restatement of Newton's second law, but for a specific case of the modified Atwood's machine. So I hope that helped you out a little bit.